Good afternoon. Today we're going to be talking about pointers in C, and this is a review of the material we had from the last week's class, and also a little bit of a preview of what's coming up this coming week. And I'm going to assume that for the purposes of this demonstration that you know a little bit about the basic data types in C, like integers, characters, doubles, and so forth. And you're also familiar with doing something like making a function and passing in values and returning values from it. So the first thing we're going to start with is maybe some diagrams here to show you conceptually what's going on. And the first thing to know is that all variables, conceptually I should say, live somewhere in memory. Where exactly they live is kind of up to the operating system and kind of up to your compiler, but they do live somewhere in memory. So for example, if you have a variable like A and B and C, they all live somewhere in memory. So let's draw them as boxes here. So here's A, here's B, and here's C, and we'll just, for the purposes of this, just arbitrarily assign some addresses. So let's say A lives at memory location 1000 and B lives at, let's say, 1020 and C lives at 1040. I just kind of made those up. And then in our program we say something like A is equal to 10, B is equal to 20, and C is equal to 30. So what that means is that in the A box we put the number 10, in the B box we put the number 20, and in the C box we put the number 30. All right, and then if we do a statement like A++, that means go into the A box and change the number that you see there, incrementing it by 1. So this 10, of course, becomes 11. All right, so that's the basics there. Maybe we can do one more. If we do something like C equals A plus B, that means go into the A box, copy the value out of there, go into the B box, copy the value out of there, and then put that add them together, and then put the calculated value in here. So we would take 11, add to it 20. The result would be 31. So we put 31 in there. Okay? So let's do another one. Now we're going to start talking about pointers. So let's say we have int A and int B. Then we have A is equal to, let's do 10 again, and B is equal to 50 this time. So I'll put A here and B, and let's say A lives at 1000 and B lives at 1020. So we've got 10 and 50. And now we define a new variable called C, but instead of just leaving C by itself, we put a star in front of that. And that means that C is the name of the variable is C, but the type is not int, but int pointer, which means pointer to an integer, or it could mean address of an integer. It could also mean a reference to an integer. There's a whole bunch of kind of synonyms we can use, but its type is no longer integer. It's now the value that's going to be stored inside the box is going to be an address, one of the memory locations. So it's going to be something like 1000 or 1020 or one of the other memory locations we've been talking about. So the statement we're going to do is C equals ampersand A. And this means, the ampersand here means get the address of, or get a pointer to A. So it's not going to be the value in the box. It's going to be the address of the box. So the value that's going to be the address of A is 1,000, and that's the number we're going to put into C. So we put in here 1,000. That's a memory location, not an integer. All right, so now if we do something like A++, well, just like with before, we're going to take the value that we find in A, and we're going to add 1 to it and change it to 11. Okay, but notice that none of the others have changed here. Neither C nor B have changed. Now let's do something, and this is where it's different. We go star C++. Okay, now what this means is go get the value of C, which is 1,000, and then the star here means go to the memory location that C points to. So C contains the number 1,000, so we're going to go to memory location 1,000, and we're going to find the value there and increment it. So really, to make this a little bit clearer, we ought to put parentheses around this to say we are going to go to the memory location pointed to by C, and then whatever we find there, we're going to increment it by 1. So this now changes to 12. All right, so one of the confusing things about the C programming language, and I'll have to admit that it took me a while to get used to this, and that is star is used 3 different ways, depending on context. So one way is it means multiplication. Another way is in the declaration of a variable, it means that variable is a pointer. And in an expression, it means dereference the pointer. Okay, so dereference, if I can switch back over here, dereference is this act of going to the memory location that the value of the variable points to. So that means going to the location 1,000. That's called dereferencing the pointer, when you follow that link back to where it goes. Okay, so it is used these 3 different ways, and it depends on context. So if it's in a variable declaration, sorry, if I switch back over here again, if it's in a variable declaration like here, it just means that this is a pointer, that C is going to contain a memory address. When it's used in an expression like this, then it means that you want to follow the link. And the way you can tell whether it's a declaration of a variable or an expression is whether there's a type out in front. See, the word int over here means I'm going to be declaring C to be a pointer to an integer. Now there's one other mnemonic that frankly doesn't work too well for me, but I've heard otherwise. I've heard other people have used, and it works for them, is to say is to actually separate out the variable name from its type. So the type here is, the name is C and the type is int pointer. And again, if you think of the star as meaning dereference, if you were to dereference something, so if you were to type star C in an expression like over here, then what this thing points to, the value that this thing points to, is an integer. Okay, so here's another way to think about this is, if I were to dereference C by putting a star in front of it in an expression, what I would get is an integer. Okay, so I personally think of C as being a pointer to an integer, but the way that some other people remember about whether to use a star or an ampersand is, in a declaration, is if you were to dereference C by putting a star in front of it in an expression like over here, then the thing that it points to is an integer. Okay, I think the stream is back again, but let me ask on chat, what was the last thing you heard? Okay, if I know what the last thing I said was, then I can kind of repeat myself. Well, I will, here's what I'll do. I'll back up a little bit. Okay, so let me talk again about variable declarations. So we have int star a. This means, so I think of this as a is a pointer to an integer. So a is a pointer to an integer, and I kind of read that backwards. But because of this confusing way that the star is used three different ways, what some people do is they actually compress down these two uses into one rule. They still have multiplication, right? That you can't really separate that out. But you have, what you do is you separate this out into one rule, and that is you still treat this star a as being an expression. It's just that it happens to have a type in front. And so one way to read this is not as the star goes along with the a, but actually the star goes along with the int. And it says that, like if you were to do an expression like just star a equals 5, okay, what that means is start at the value of a, which is a memory address, dereference it, so go to that memory location, and then store the number 5 there. So in other words, if you follow the link from a, what you will get, the thing it will point to, is an integer, like the number 5. So they read it this way here. They say, if you were to dereference a by putting a star in front of it in the rest of your program, what you would get back is an integer. Okay? That works for some people. That definition doesn't work too well for me personally, but it does work for other people. And I think it makes a little more sense once you start seeing some more complicated declarations here. But again, it means that if you were to take a and dereference it, what you would get is an integer. Okay, so what I want to do now actually is show you some interactive examples of this idea of pointers. So let me switch screens over here. Okay, and I've got a program on the screen. It just declares two variables, a and b, and sets their values to 100. And it declares a variable called c that is a pointer to an integer. And then what it does is it says the value of c is going to be assigned the address of a. So wherever a happens to live, that's going to be the address that we put in c. Then we're going to change a, and then we're going to sort of indirectly change a by following the pointer from c to a and then changing the value to 30. Okay, so you have to kind of take it on face value this works, or I can actually show you interactively that this is the way it's working. So the way we do this is we need to compile the program just like we do before. So we invoke the C compiler on the C program, we output to an executable, but we're going to add one last flag on there, which is -G, and that tells the compiler to, in essence, embed the source code of the program into the executable. So it produces an executable that's a little bit bigger because the source code is essentially in there, but it runs just the same. And now, if I run this program, nothing's going to happen because nothing gets printed out at all in this program. But if I invoke what's called the debugger, and here it's called GDB, the GNU debugger, and I give it the name of the program I want to debug, which is pointer 2, first thing I get is a whole bunch of kind of copyright information. You can ignore that, but at least it's not important for what we're doing. And then we come down to a prompt, and here there's a whole bunch of commands we can type in, but the two we're going to use are L and P. L means list the program, and it shows us our program listing. And then P means we want to print out an expression, and actually there's a third one we're going to use, which is B, which is we're going to set what's called a breakpoint. So if I say B5, what it's done is it's set a breakpoint at line 5, which is this one. And a breakpoint means the program is going to start running and then it's going to stop at line 5. And it's not yet going to execute line 5. It's going to stop there and wait for us to do something. So at this point, we'll type R for run, and you can see it has stopped at line 5. And I'm going to print the value of A, and we can see it's 0, and B is some value. These are actually two garbage values. These are the values of A and B before they've ever been assigned. So now we're going to use another, I said we're going to use two commands, and sorry, that was a total lie. We're going to use like 8. So there's P for print, L for list, R for run, B for set a breakpoint, and there's another one called S, which stands for step. We're going to step to the next instruction. So we're going to step ahead, and it stops now on line 8, which is this one, which is the first statement where something is actually, next statement where something's actually happening. And now if we print the value of A, we'll get 10, which is what we would expect. And if we print the value of B, we get 100. So that's the result of executing line 5. Okay, but if we print the value of C, that's actually a junky value at this point. Another thing we can do is we can print out the address of A, P ampersand A, and we can see that A actually lives at this address, and this is a hexadecimal value. It's a pretty high number. It's like up in the 3 billions or so. But let's just use like the last 3 digits as the memory location. So A essentially lives at memory location 194, and B lives at 190. So it's actually a memory location that's a little bit previous to it. And actually the difference is 4 bytes, and that's because A and B are both 32-bit quantities, 4 bytes, 8 bits per byte. So you get 32 bits, and so that means A and B are actually sitting right next to each other in memory, separated by 4 bytes. Okay, see, where do we leave off? Okay, so we set a breakpoint on line 5. We stepped forward to line 8. A lives at 194. B lives at 190. The value in A is 100. The value in B is, the value in A is 10. The value in B is 100. And now we're going to step forward again. And now we have executed this instruction. So put into C the address of A. So if we print C now, we can see its value is 194, which is the same as the address of A. And now we're going to step forward again, and we've now just executed this instruction. So if we print A, we get 20. If we print C, it's still 194, but if we now print star C, which dereferences C, which now tells it go to memory location 194 and look what's there, we can see it's 20. That's the value that was in A. And B remains unchanged. And now I think that was, so let's do another step. So now this is the end of the program, and it has now executed this instruction. So if we print the value of C, it hasn't changed at all. It's still 194, because what we're saying here is go to the memory location pointed to by C and set the value to 30. So if we print A, it's now 30 because C was pointing to A. And if we print star C, that's also 30 because C is also pointing to A. So C is pointing to A. A has the value 30. So if we print out A, we get 30. And if we print out star C, we also get 30. Okay. So you kind of see what's going on there. I get Q to quit out of that. And we're back to this program over here. So let me make let's make a function up here. Let's go void, it's called f. This is a function called f. And it takes in a single parameter called x, and let's go x equals 90. Okay, that's all it does. And let's erase this stuff here, and we'll go f of a. Okay, so in our main, we're going to call f with the value that's in A, which we know is 10. Okay, so let's see what happens. Let's save this, and we'll switch back over to here, compile it, and then run it. Okay, and let's set our breakpoint at 11, which is this statement here, and we'll run the program. And we'll go step and step. Okay, so at this point, A has a value of 10, B has a value of 100, C has the value of 194, which is the address of A, and we can verify that with print address of A. And now we're going to step, and we're going to find ourselves at line 5. Line 5 is the assignment statement inside of F. So again, it hasn't executed this statement yet, so let's print the value of X. And we see that it's 10. So this is the value that came into F from main by passing the value of A. Okay, so the value of X has taken on the value of A. And if I do a step again, I'm now on line 6, so I'm here. That means I've done this assignment. If I print the value of X, it comes out to be 90, which is what we would expect. If I print the value of A, we're actually going to get an error because inside of this function called F, there is no variable called A. A doesn't exist. So there's only one variable visible to this function. It's called X. A isn't visible at all. But if we step again, we're now back in main. You can see that by line 17. If I list the program out, that's essentially the last line of the function. So if I now print the value of A, it's still 10. Okay, so A hasn't been changed at all. And let me see if I can draw a picture illustrating why that is. Okay, so in my program here, here's main, and there's a variable called A, and there's a variable called B, and there's a variable called C. And inside A was 10, inside B was 100, and C we saw was 194, which is the address of where A lives. And then we call, sorry, I said foo, that's not what it is, it's just F. And then we call a function called F. And inside of F, there is a variable called X. And this is actually a parameter to F, so let's do it like this. Okay, let's put X here. I'm going to draw a red line. The red line, so what I'm saying here is that the stuff above the red line are parameters that are going in, and the stuff below the red line would be variables that are internal to F, which we haven't declared any, but you can see where I'm going to go somewhere with this. Okay, so what happens here when you call F from main is and remember what we did was we went F of A, which really means what we're doing is F of 10. Okay, so what's happening is when we invoke F and we say give it the value of A, it goes and it looks for the value stored in A, it comes up with 10, and it plugs that in as the parameter to F. Okay, so that number 10 then goes up into F and appears as the value of X. So here's the important thing, is that X and A are two totally independent variables. What the computer is doing is it's taking the value of A and making a copy of it and putting that into X. Okay, this is really important, that this is a copy of A. It's not A itself. It's a copy of A. And what that means, because it's a copy, is that f is then free to go and change this value. And since it's a copy, it's not going to affect the original. And we saw that in the program. We attempted in the program to change this value to 90, and then we saw it does not change the value inside of A. Okay? And it's all because the computer makes a copy of the values being passed in. Another way to say that is, if we were inside of F and we tried to investigate where this 10 came from, we would have no record of where it came from. All it sees is the number 10 coming in, and F has no idea that that originally came from A. No idea at all. Okay? So now, let's go back to the program and let's make a change to it. Okay, so now let's say that f doesn't take in an integer, but rather it takes in an integer pointer. And because x is an integer pointer, we can't just say x equals 90. And the reason for that is that there's a type mismatch. X is an integer pointer, and 90 is an integer, and you can't assign an integer to an integer pointer. So to make the types match up, we have to put a star in front of the x to say the thing that x is now pointing to is an integer, so star x, its type is int, and 90 is an int, so we can make that assignment. And then when we call f, we can't just say a, we have to say the address of a. Okay? And now, if we save this, and we run this, so let's do it. Let's clear this first, compile it, and we run it. And we'll do a breakpoint on line 11 like we did before. Okay, step, step. So if we print C, 194. If we print A, it's 10, and B is 100. Now if we go we'll do a step, and now we're inside of that function called f. And if we print the value of x, we can see it's now no longer the number 10, it's now 194, which means it has picked up the address of A. If we print out star x, it'll show us that x can, if we follow x's pointer, it goes back to A, which pulls out the value number 10. And if we step again, we've now done that assignment. We've done this one right here. Okay? So if we print the value of x, it's still 194. If we print star x, it's now 90. Okay, so that kind of makes sense from this statement here. So we'll step again, and now we're inside of main. So if we print out A, we'll see that its value is now 90. And if we print out B, it's 100, and C is still 194. So the only one that changed here is A. So this is different from what we had before. What we had before was we changed X, and it didn't affect A. And now, well, it appears like we're changing X, but we're not changing X. But now we have a function that's able to go and affect the value of a variable somewhere else in the program. Okay, so let's now draw a picture for that. I think I can just modify the one that I've got here. All right, so I've still got A, B, and C, same values as before. And now what I'm saying is F has an input called X that's an integer pointer. And then I do F of the address of A, which really means what it's going to do is it's going to evaluate this ampersand A, which is 194, and plug that in for the parameter. And then that number is what goes up into here. Okay? And again, this is a copy of the address of A. So before it was a copy of A, and now it's a copy of the address of A. So this 194 is the number that goes up into here. And then inside f, I say star x equals 90. And that tells it, okay, go to the thing that x is pointing to. So it reaches down and goes into memory location 194, and it stores the number 90 there. All right, so it's now able to, by getting the address of a variable rather than the value of a variable, it's able to reach into a different function and change the value of that variable. All right, and it's all because the compiler looked up, the address of A, found that number, and that number is then copied into the parameter x, or star x in this case. And then because x contains the address of a variable, it can then go and change that variable itself. All right. So let's see, where do I want to go from here? So it's also important to realize that this is still a copy of the address of A. Okay, if my function here actually changed the value of x, let's say it went and did something like x equals and then something else that was evaluated to a pointer, that would not change at all A, B, or C. All it does is it changes the number that's being stored up in here, and it doesn't then go and affect anything else. Okay, and it's all because this is still just a copy. Now, if you read a textbook on this, and most textbooks will say this is called call by reference, as opposed to call by value. Okay, call by value is what we had on the previous slide. Call by reference is supposedly what we have by now. That's actually not entirely true. So it is true that in fact what you're being passed is a reference to a variable, but you are actually being passed a copy of it rather than the variable itself. Okay, so this is not really call by reference. What this actually is, it is call by value of reference. Okay, it's actually a hybrid of both of them. What we're doing is we're finding a reference to a variable and then calling it by the value of that reference. And when we call by value, you make a copy. And when you call by reference, you don't make a copy. This is the important thing. When you call by value, you make a copy. And when you call by reference, you don't make a value. But in fact, here we are. We're making a copy. So it's actually the value of the reference. There's very, very few programming languages out there that actually do real call by reference. And in real call by reference, what would happen is x would be an alias for A. And the function f would just think, oh, it's an integer. It's not necessarily a pointer, it's just an integer. But if it went and changed x, it would also change A. Okay, there's very few programming languages that do that. Almost all of them, when you call a function, it makes a copy of some kind of value, so that that function goes and modifies those variables. It isn't affected outside of there. Okay. All right. So let's see. No pun intended. So this sort of thing of passing in a pointer to an integer is, let me switch back over here. This thing of passing in a pointer to an integer is commonly done when a function needs to return, let's say, two different values. So as you know, a function can only return one value. It can return a single integer or a single string, but it can't really return more than one value. So a common way to do that is for at least one of the things you want to return to be a parameter for which you're getting a pointer to. Let's see if I can come up with an example for that. It's hard for me to come up with an example right on the spot that's just short and quick. So how about this? So just to reflect back on what we already know, if we do something like scanf %d, comma, ampersand a. Okay, so now, before I've always just said, you got to put an ampersand in front of these variables just because. But now it should become clearer why we're putting an ampersand in front of these variable names. It's because scanf needs to be able to reach back into our main and change the value of A. All right, so this is why we're giving scanf the address of A, is so that scanf can go and change our A variable directly. Okay, and then you may be wondering, why doesn't scanf just return an integer? Why can't we just go A equals scanf %d or something like that? Because scanf is only returning one single value, we can just assign it. And that's for two reasons. One is with scanf, as you know, we can actually read in like two numbers. Okay, so we want to be able to return multiple values from scanf, and the way we can do that is by passing them in separately as their addresses, so that scanf's job can be to modify the values directly inside the variables that are inside of main without actually knowing the names of the variables themselves. All it knows is that it's got a memory location to go change and another memory location to go change, and it just changes them. The other reason for this is because scanf actually does return a value. Scanf is defined to return an int, and that int, in fact, is the number of variables it's successfully able to read into. So, for example, if I do this scanf and I only type in one number instead of two numbers, scanf will return a 1, indicating that only one variable was read in. Or a different reason would be if I type in two numbers but I botch one of them. Let's say I type in the number 5 and then I type in the word hello. Then scanf will come back and say it was successfully able to assign the value of A, just one of them, but not the value of B. And so it would return the value of 1, indicating only one variable was successfully read in. And so the return value from scanf is actually sort of an error code or a status code that tells you how successful it was in doing its job, and then the values of the variables themselves are passed in as addresses. Could I please name a couple of programming languages that real call by reference? Not off the top of my head. I think if you Google for that term, call by reference, then you might come up with a language that does it. Let me try it, actually. So I'm just scanning through here. Unfortunately, most web pages you come across are going to say, hey, C is call by reference, but it's not. It's called by value of reference. I was going to say that maybe C++ can perhaps do sort of a pseudo call by reference. But I'm thinking that when I said really few languages actually do it, it's like so few that you're probably not going to recognize the languages, the names of the languages that actually do it. And I'm coming up a little blank right now. I mean, it was so rare that when I read about it, it was like, I hardly know that language either. There's a comment here: Java objects get passed as reference. So it's true. In Java, you're also passed the value of a reference. And in fact, in Java, there's only like 6 or 8 data types. There's the primitives: int, boolean, byte, double, and so forth. And then there's everything else, which is just objects. And objects are always passed by their addresses, and the primitives are always passed by their values. Okay, but in Java, they're passed by the value of their references. They're not a reference to the objects. They're not the actual objects themselves. Which is, I mean, it's really done for efficiency's purpose. The reason for that is when you pass in an object, you're actually passing in the address of that object, and that of course makes it faster because all you're doing is you're passing like a 32-bit number into that function rather than making a copy of the entire object, which could be really huge. The downside of that is that once the receiver of that object gets the reference to it, it kind of can do whatever it wants. It can call any of the methods on that object, particularly if it does something like it gets an array from a caller, then it's free to go and modify the array however it wants. It can go and just change some of the values in the array, which is probably what you want to do in most cases, but it may not be something you want to do in certain cases. Like if you're writing, let's say, software that needs to be secure and you're doing something like a username and password lookup, what you might think you want to do is maybe pass the username and password or something like that as an array to a caller. But now what that caller can do, now that they have the array, is go and modify it so they could actually go and change the username and they could change the password if they wanted. So you have to be very careful if you want to, particularly with arrays, if you want to pass an array to another method and you want to make sure that that method does not change the array at all, what you actually have to do is make a copy of the array and pass that array itself. And so this is a shortcoming of Java's approach of primitives are passed by value and then everything else is passed by its address. Sorry for distracting. That's no problem. You're free to ask questions here. I encourage these types of questions. I did a quick search for it, and unfortunately, all the pages that came up for me all insisted that Java and C pass by reference, and it's actually not quite the case. All right, so back to our C program here. I guess we're rapidly kind of approaching the end of what I wanted to do here today, but I basically wanted to make the point here, which is it's common for a function. Let's say we have a function called ReadFile, okay, and you want to be passed in the. Let's see, what should ReadFile do? You probably want to pass in, let's say, the name of the file that you're going to read. So that would be passed in as a string. Let's call this fname. And then what ReadFile is going to do is it's going to, let's say, put the contents of that file into a string of some sort. And so I'm not really going to fill in the contents here of how this function is going to work. But let's say you're passing a file name, and you also want to be passed in a pointer to, let's say, a string where the content of the file is going to go. And because in C you don't know the length of an array, you don't know the length of a string necessarily, you might also have to pass in a pointer to a variable representing its length. And then what ReadFile is going to do is it's going to open fname for reading. I'm just putting in comments here. Read the file into the string, and then set the length of str by assigning to len. And so what this ReadFile will do is it'll go star len equals, and then some number or something like that represents the actual length of the string or length of the file. And then whoever calls ReadFile down here would do ReadFile input.txt, and let's say they also have a character array. So we go f, and we have length of f. All right, so when you call ReadFile, you're going to pass in a string, an array where the results are going to go, and then a variable that holds the length of that string so that whoever then goes on and uses this string knows how long it's, I keep saying string, but I want to say like just an array of bytes, knows how many of those bytes are actually valid. Okay, and this is all because C doesn't know the length of arrays. You can't ask this f array how long it is. So what you have to do is pass in an integer that will hold the length and then have that function go and assign to it the length. Okay, that number is way too big, but let's say it's that. Okay, in that way, later on you can do something like for int I equals 0, I is less than length of f, I plus plus. Do something to each character of f. Okay, and so that's how you can make sure that you're only acting on the actual valid bytes that are in the array. So I guess the last thing to bring up is, how come when I called ReadFile, I had to put an ampersand here, but I didn't have to put an ampersand here, and certainly none here, even though every single one of these parameters has a star in front of that. Okay, and that has a lot to do with the fact that, let me switch screens over here. So in C, arrays are known by their addresses. Okay, so let's say I have int ARR bracket 5. What this says is ARR array is an array of 5 integers. 1, 2, 3, 4. Okay, so this array lives somewhere in memory, and let's say the first box lives at address 1000. That means the next box is going to live at address 1004, because each one is an integer, and I'm assuming integers are 32 bits. So each one is going to occupy 4 bytes. The next one is 1008, 1012, 1016, and so forth. Okay, so if I was to ask, what's the value of ARR just by itself, it would say 1000, because that is the address of the first element of the array. Okay, in fact, let's try it out. I bet you we can. Let's go and modify our program here. I want to get rid of all this. Don't need that. Let's go ARR bracket 5. So A equals 10, B equals 100. And we'll go ARR bracket 0 equals 50. ARR bracket 1 equals 60. All right, we'll do that. Okay, list our program. So we'll break at line 8, run it, start at A equals 10. Actually, we can't really break at line 8 because these really aren't executable instructions. They're just declarations. So the first place we're actually going to stop is line 11. We'll go step and step. So we print A, we get 10. B is 100. And if we print ARR, well, it says incomplete. This is oh, you know what? This is GDB trying to help us here. If we say print the address of ARR, we come up with this here. BFFFF of 18B. But it so happens that these two should be the same. Okay, and actually I have a different tool available that illustrates this a little bit better. Let me see if I can bring that up here. So this is called cint. This is interactive C, and I'm not going to say at all that this is a production ready tool. In fact, I found this tool, and there's a note at the bottom that says this is no longer maintained. Please don't use it anymore. But I went and tried it anyway, and it's kind of cool because it's sort of like a C interpreter. You can type in C statements and see what happens, and you don't have to compile anything. So like I can go int a equals 10. You put it inside of braces and it executes those things. And then I can say print the value of a, and it says it's a 10 and it's an integer. So I can go int arr5. Okay, and if I print arr, it says that arr is actually a pointer to an integer, and here is its address, 239C890. And if I print the address of arr, I get the same thing back. So in C, for an array, the value of the variable for the array and the value of the address of the variable for the array are the same thing. So this is kind of something a little bit weird in C. Obviously, it doesn't hold for the primitive types like integer itself or character or double. But for arrays, the value of the array variable and the value of the address of the array variable are the same thing. Okay, so if I go arr bracket 0 is equal to 50. Oh, I have to put it in braces. Arr bracket 0 equals 50. And I go bracket arr bracket 1 equals 60. And if I say print arr bracket 0, I get 50. Bracket 1 is 60. If I say, tell me the address of the first element of the array, I get 239C890, which is the same thing as the array itself. Okay, and if I say print the address of the number 1 element of the array, you can see it's 4 bytes higher because it's 32 bits. Okay, and here's the address of the number 2 element of the array. It's 4 bytes higher than that. Okay, and if I say, tell me what's there, some junky value. But, whoops. But 1 is, whoops, sorry, print AR1, here we go, is 60. Okay, so this is the important thing, is that arrays are, if you pass in, or I should say, let me back up, if you pass to a function an array, what you need to do is just put in the name of the array, and what will actually get passed is its address, the address of the first element of the array. So when you're calling a function in C, let's say I have a function, void f, that needs to be passed in this array, what I would say is int pointer, let's call it x. Okay, this is another way to do it. So I can do it either this way, which says that x is an array of integers, or I can just say star x, and this works just fine because what's going to be passed in down here, if I say f of arr, is it's going to look up the address of the first element of the array. It's then going to copy that value and pass that in and put that into x. And since x is expecting an address, then that type checks. So then I can say x bracket, let's say 2 is equal to 99. And since x is an address, it'll then go to box number 2, change it to 99, and then this function is done. So let's save it. And we'll clear. What happened here? Oh, I made that a character. That should be an int. That was actually a type checking error. Okay, list the program. Let's break at line 14. We'll run it. So you can see the ARR currently consists of junky values. Step, 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 step. Okay. Now ARR contains 50, 60, and 3 junky values. A and B are 10 and 100. And then if I go step, I'm now inside of the F function. So if I print x, we can see its value is not the array, but its value is just the address that we were passed. If I print x 0, I get 50. My cat is wanting to be fed, if you can hear her. There's x of 1. X of 2 is that junky value, this one here. Okay, but if I step and assign x of 2 to 99, then if I print it out, I get 99. Okay, and I step again, and now I'm back in the main. And if I print ARR, I get 50, 60, and 99. So my program called the f function. I just pass in the name of the array, and what actually goes in is the address of the first element. And then inside the function, I set it up to receive an address, and then I can access it just like an array. Okay, but there's something else you can do here. Let's run the program again. Okay, step, 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 step. Okay, I'm going to step one more. Actually, I'll stop here. What happens if I go ARR bracket 9 equals 45? So what I'm doing is I'm trying to access box number 9 of the array, and the array only holds 5 numbers. Oops, sorry. Let's see. I'm not actually sure in GDB how to assign something. Well, so let's do it in the program itself. Let's go ARR bracket 9 equals 45. Save it. Huh. Well, okay, I get a warning there, but we'll ignore the warning. Okay. Break at, what was it, line 14? Step. No, run it. Step, 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 step. Okay, if I print out ARR, I don't see those things. If I print out ARR bracket 9, we can see there's a 45 sitting there. All right? So in C, arrays are not bounded at all. You are totally free to set whatever element of an array, even if that element is off the end. And C will not do any kind of bounds checking as the program is being run. It will just gladly go and assign to box number 9, even though the array contains only 5 things. And the same thing can happen over here. I can say assign to box number 12 the value 101, and it will go and gladly do it. Okay, and this all has to do with how arrays are indexed. Okay, so let's say I do ARR bracket 2 is equal to 99. So the calculation it does is it goes and it picks up the value of ARR, which is, sorry, this is 100, and then it adds on 2 times 4. And this number 4 is the number of bytes used by an integer. Okay, so it starts with a base address, which actually should be 1,000. So the base address of 1,000, it adds on 8, and it goes to the memory location 1008, and then puts the number 99 there. Okay, that's how array indexing works. It's actually behind the scenes just doing this calculation. So let's say we go ARR bracket 8 is equal to 101. Well, it does the same thing. 1,000 plus 8 times 4, which is 1032. So then it goes into memory, and it goes all the way off to box number 1032. And it puts the number 101 there, which is off the end of the array, but it's perfectly fine in the C programming language. So C doesn't protect you at all from walking off the end of an array. It will just go and do it. And it's all because It just simply does this calculation, and there's no bounds checking. Now, other programming languages do have bounds checking. You know, Java, C++ to some extent. Most other, let's see, what others? Python does bounds checking. I think PHP does it also. And so that means every single array access like this needs to be wrapped up inside of an if-else to make sure that this number, this number here, this total number doesn't go off the end, and it slows things down. So that's the trade-off. You get a little bit extra protection, but it's a little bit slower. In C, we want to go as fast as possible, so we don't protect you. Okay, so let's see if I can just kind of summarize. Okay, so to declare, a pointer, you do something like int star x, and it means x is a pointer to an integer. To get the address of a variable, you say ampersand and that variable name. Let's use I in this case. To dereference a pointer in an expression, you say star x. And that means go to the memory location that x points to. To pass a pointer to a function, what you need to do is make sure that the value you're passing into the function is a memory location. So we can call f of the address of I. That's one way to do it. Or we could just say f of x. Since x already is an address, this type text just fine. Okay. Arrays are known by their address. So if we say int arr bracket 5, the value of arr is the address of the first element. Okay, so when you want to pass an array to a function, you don't have to get the address of the array because the variable name already is an address. So to pass an array to a function, just use the variable name because it is already an address or a pointer. Okay, and then to receive an array, either use array declaration or use pointer declaration. Okay, and I'm running out of space here, so I'll see if I can squeeze this in at the very bottom. I can either say f x, sorry, let me back up a little bit. Int x array. So I can either do this. I can say that f is a function that receives an integer array known as x, or I can say f int pointer x, and this says f is a function that receives an address, and it's just going to be assumed that it'll be an array. Okay, so in this first case here, f is able to tell that x is an array because you're using this array notation. In this second one down here, f has no idea that x may or may not be an array. All it knows is that it's a memory address. And if you use it like an array, it'll go ahead and do that calculation like I showed you and store the number there. And if you just use it like a regular pointer, where you just like assign a value to it directly, it'll just assign it. It has no idea whether this is actually an array or just simply the address of a single number. They're both, to the C programming language, the same thing, and it just has to do with how you end up using them. So in your program, again, let me just summarize. If in your program you did, I don't want to point to my head. Let's point way up here. If I said star x equals 5, then what it would do is go to the memory location pointed to by x and put the number 5 there. And if I did x bracket 2 equals 5, it'll do that calculation where it takes 2, multiply it by the size of the integer, and add that to the base address and put the number 5 there. And if I do x bracket 0 equals 5, this ends up actually being exactly the same as the top one, because it just assigns to the first address of the array. This is essentially the first address of the array. Okay, so in C, when you're passing an array into a function, all you have to do is give it the name of the array, and the address of the first element will automatically go in. And when you're receiving the value, you can either say it's an array, or you can just say it's a pointer. And actually, the second one here is the more common way to do it, is to say you're just going to receive a pointer, and it's up to, in the documentation, to explain whether it's supposed to be an array or it's supposed to be just a standard pointer. All right, so I think that is enough for today. It's been a little over an hour or so. So we did a review of what we did last week, and we also previewed a little bit about this coming week, which has to do with passing the arrays in to a function. And what I'll do is I'll stick around for about another minute and see if anyone posts any more questions in the chat. Otherwise, if I don't hear anything, I will bid you farewell for now, and then I'll see you next time. All right, well, I don't see anything. So I think that's it for this week. And again, I'll see you next time. Actually, I'll stick around in the chat for a couple more minutes even after the stream ends. So if you want to ask a question, if you got a last minute one, then I can answer it right there.